Welcome back to the deep dive. Today, we're going to be exploring something pretty fascinating.
Oh, yeah.
Yeah, AI's role in mathematics.
Huh?
Specifically, we'll be looking at a pre-publication research paper all about formal mathematical reasoning.
Interesting.
Now, I know that might sound a little bit intimidating,
Right.
but stick with us. This stuff is really mind-bending.
I'm excited.
So just a little fun fact to kick things off.
Okay.
Did you know that the very first AI program ever created was designed to prove mathematical theorems?
Wow. No, I did not know that.
It's true.
That's pretty cool.
But the way AI approaches math today is way more sophisticated
Oh, I bet.
than just, like plugging in numbers and spitting out answers.
Right. Right.
So let's set the stage here.
Okay.
Broadly speaking, there are kind of two ways AI is being used in math.
Okay.
The first is what we might call the informal approach.
Okay.
Think of it like high school math.
Okay.
You have a problem.
Right.
You use formulas and steps to solve it, and you get a nice, neat numerical answer. And the paper we're looking at actually gives a really great example of this.
Okay.
An AI system called Math.
Okay.
And this AI actually won the AIMO Progress Prize,
Wow.
which is a pretty prestigious math competition.
That's impressive.
So could you walk us through how this informal approach works in practice?
Sure. So, in essence, these AI systems are trained on just vast amounts of math data.
Oh, wow.
Imagine feeding a supercomputer every math textbook, every online forum discussion about math, you name it.
Okay.
This is called the math pre-training stage.
Right.
And it gives the AI this really broad understanding of mathematical concepts.
So it's like giving the AI a crash course in all things math.
Yeah, exactly.
Okay.
Then the AI goes through a fine-tuning process.
Okay.
Here, it's trained on specific types of math problems,
That's
learning from step-by-step solutions that are provided by humans.
okay.
And it's not just about getting the right answer, it's about learning the logical steps and strategies involved in actually solving the problem.
So it's learning to think like a human mathematician.
In a way, yeah.
That's wild.
And then to help it along, AI often has access to tools like calculators or software for symbolic manipulation.
Mhm.
This is called tool-integrated reasoning.
Okay.
And it allows the AI to tackle complex calculations and symbolic operations.
This Math AI sounds incredibly advanced.
Yeah.
But I'm curious, though, what are the limitations of this approach?
Hmm.
Because I imagine there must be some.
Yeah, you're right. There are some inherent challenges.
Okay.
One major hurdle is data scarcity.
Okay.
As you move beyond, high school math, the pool of neatly organized problems with step-by-step solutions, it starts to shrink.
Yeah.
Finding enough high-quality data to train AI on more complex math becomes incredibly difficult.
Yeah, that makes sense. It's probably a lot easier to find solutions for algebra problems online than it is for, advanced calculus or topology.
Exactly.
Yeah.
And here's the other big issue. Verifying correctness. In simple math problems, the answer is often a straightforward number.
Right.
But in advanced math, solutions are often these complex chains of reasoning like proofs. And it's not always easy to tell if the AI's reasoning is truly sound or if it's just spitting out something that looks plausible.
So how do we overcome these limitations?
Yeah.
That's where this idea of formal mathematical reasoning comes in, right?
Precisely, the formal approach addresses these issues head on.
Right.
It's like a game of chess. Every move has to be legal according to the rules of the game.
Okay.
In formal math, every step in the reasoning process must be verifiable based on a specific set of rules and logic.
So it's a much more rigorous and precise way of doing math.
Yes.
And you're saying that almost all of mathematics can be expressed using this formal logic.
That's right.
That's incredible to me. Centuries of mathematical knowledge, all built upon this foundation of logic.
It's remarkable.
Yeah.
And to help us navigate this world of formal math, we have these incredible tools called proof assistants.
Okay, proof assistants. Those sound intriguing.
Yeah.
Is it like having a personal math tutor built into your computer?
In a way, yes.
Yeah.
Proof assistants are software tools that are designed to help humans write formal mathematical proofs.
Okay.
They act as a kind of interactive guide,
Okay.
making sure that every step in the proof follows the strict rules of the system. The paper focuses on one particular proof assistant called Lean,
Okay.
which has become increasingly popular among mathematicians.
So I'm intrigued.
Yeah.
Can you give us a simple example of how this process of formalizing math in Lean actually works?
Sure. Imagine we're trying to prove a very basic theorem. Let's call it the add zero theorem.
Okay.
It just simply states that adding zero to any number doesn't change that number.
Okay. Pretty obvious.
Right.
Yeah.
So in Lean, we would start by formally stating this goal.
Okay.
Then we apply what's called a tactic.
Okay.
A tactic is like a strategic move in chess.
Gotcha.
It breaks down our goal into smaller sub-goals.
So we're breaking down a complex proof into manageable chunks.
Exactly. We keep applying these tactics step by step until we reach a point where the proof is self-evident.
Okay.
Each step is checked by Lean to ensure it's logically sound according to the rules we defined.
So it's like solving a puzzle, but each piece has to fit perfectly logically.
That's a great way to put it.
Yeah.
And what's fascinating is that writing these formal proofs in Lean feels very similar to software development.
Oh, really?
You have libraries of pre-proven theorems. You can build projects.
Wow.
And there's even this massive online library called MathLib with thousands of theorems that have already been formally proven.
So it's like open source mathematics where mathematicians from all over the world can collaborate and build upon each other's work.
Yeah, exactly.
That's really cool.
It is.
All right, so we've got these proof assistants like Lean that help us navigate the world of formal mathematics.
Right.
But how does AI fit into all of this?
Well, there are two key areas where AI is really starting to shine in formal math. Autoformalization and neural theorem proving.
Okay, let's unpack those.
Sure.
What exactly is autoformalization?
Imagine you have a notebook full of your messy, informal math scribbles.
Yeah.
Autoformalization is like having an AI translate those notes into perfect, formally correct Lean code.
Oh.
It's like a super-powered translator for the language of mathematics.
That would be incredibly useful. I can imagine that would save mathematicians a ton of time and effort.
Oh, absolutely.
Yeah.
And the techniques for doing this have evolved significantly. Early attempts use rule-based systems, but more recently, large language models, LLMs,
Right.
which are trained on massive amounts of text data.
Yeah.
They're showing real promise in tackling this auto-formalization challenge.
So it's like taking the power of AI language translation and applying it to the world of mathematics.
Precisely.
That's really cool. And what about neural theorem proving?
Yeah.
What does that involve?
So neural theorem proving that's even more ambitious.
Okay.
It's about creating AI systems that can actually discover proofs for new theorems.
Right.
Just like a human mathematician would.
Okay.
It's still early days, but
Right.
AI is learning from human-written proofs to get better at this incredibly complex task.
So we're not just talking about AI understanding math. We're talking about AI contributing to new mathematical knowledge.
Exactly.
That's a huge leap.
Yeah, it is, and the implications go far beyond just proving theorems.
Oh, tell me more.
Well, imagine an AI that can help ensure the information we encounter every day is logically sound.
Okay.
Think about all the news articles, social media posts,
Right.
scientific studies, even political arguments we're bombarded with.
Yeah, for sure.
Wouldn't it be amazing if AI could help us determine whether those claims hold up to logical scrutiny?
That would be incredible, especially in today's world where it's so hard to distinguish fact from fiction.
Right.
It's like having a built-in BS detector.
Exactly.
I like that.
And that's just one example.
Yeah.
Think about software development.
Right.
Imagine AI helping us write code that is completely bug-free because the underlying logic has been formally verified.
Wow.
That would revolutionize industries like aerospace, finance, healthcare.
Those are some seriously high stakes.
Yeah.
So we're not just talking about abstract math problems here,
Yeah.
but real-world applications that could have a huge impact on our lives.
You got it, and that's why this field is so exciting.
Yeah.
It has the potential to not only advance mathematics, but to improve the reliability and safety of the systems we rely on every day.
So it's clear that AI for formal math has huge potential.
It does.
But what are some of the challenges that researchers are still working to overcome?
One of the biggest challenges is still data.
Okay.
Remember how we talked about the importance of data for training AI systems?
All right.
Well, in formal mathematics, we just don't have enough high-quality, formally verified proofs to train these systems effectively.
So it's a chicken and egg problem.
Yeah.
We need more data to train the AI. But creating that data is a slow and laborious process.
Precisely. But researchers are exploring some creative solutions.
Okay.
One approach is to leverage the vast amount of informal mathematical knowledge that's out there, like textbooks, research papers, lecture notes,
Right.
and use AI to translate that informal math into formal, machine-readable proofs.
So it's like auto-formalization on a massive scale.
Yeah.
Using AI to bridge the gap between the informal world of human mathematics and the formal world of computers.
Exactly. If we can successfully translate even a small portion of this informal data, it could have a snowball effect.
Oh, wow.
The AI can learn from those translated proofs and get better at auto-formalization,
Okay.
leading to even more data and further improvements.
That's a really clever approach.
It is.
Are there any other strategies being explored?
Another intriguing approach is to use the formal systems themselves to generate synthetic data.
Okay.
Imagine an AI creating its own math problems and solutions, all within the rules of a formal system like Lean.
Wait, so AI isn't just learning from existing math, it's actually creating new math.
It is.
That's mind-blowing.
And it's not just a theoretical concept.
Huh?
This approach was successfully used in the Alpha Geometry project,
Okay.
an AI system that specializes in solving Olympiad-level geometry problems.
Wow.
It was trained entirely on synthetically generated data and achieved remarkable results.
So instead of relying solely on human-created data, we can use the power of AI to explore a vast universe of possible mathematical theorems.
Exactly.
That opens up some incredible possibilities.
It does.
We've talked a lot about data,
Right.
but are there any other challenges in this field?
Absolutely. Besides data, we also need to develop better algorithms that are specifically designed for the unique challenges of formal mathematical reasoning.
So it's not just about feeding these AI systems more data, but about developing smarter algorithms that can truly understand and work with complex mathematical concepts.
Exactly. One area of active research is in proof search algorithms. Remember how we talked about those tactics in Lean, those strategic moves for breaking down proofs?
Right.
Researchers are developing algorithms that can help AI systems find the most efficient sequence of tactics to reach a proof.
Gotcha.
It's like giving the AI a roadmap for navigating the complex world of formal mathematics.
So it's like chess, but instead of moving pieces on a board, the AI is moving through a space of logical possibilities, trying to find the path to a valid proof.
That's a great analogy. And another exciting area of research is in library learning.
Okay.
The idea here is that AI can not only learn from existing proofs,
Right.
but also contribute to the growing library of mathematical knowledge by adding new theorems and definitions.
So we're talking about AI not just solving math problems, but actually expanding the very language of mathematics.
It's a truly ambitious goal,
It is.
and there are still many hurdles to overcome,
Right.
but the potential is enormous.
So we've got this incredible potential, but also these significant challenges.
Yeah.
How do researchers measure progress in a field as complex and ambitious as this? What are the milestones they're aiming for?
Well, one way to track progress is to focus on specific tasks like theorem proving and auto-formalization.
Okay.
The research paper actually proposes a set of capability levels for each of these tasks.
Okay.
It's similar to the levels of automation we use for self-driving cars.
So it's a step-by-step progression from basic capabilities to more advanced levels of AI mastery.
Precisely. For example, in theorem, proving the most basic level is simply being able to verify a formally correct proof.
Okay.
This is something that current proof assistants can already do quite well.
So that's like the baseline level of competence for AI in formal math.
Right.
What about the higher levels?
The next level up involves AI systems that can assist humans in developing proofs.
Okay.
This could involve suggesting potentially useful definitions, lemmas, or even complete proof steps.
Gotcha.
It's like having an AI research assistant working alongside a human mathematician.
That sounds incredibly helpful.
It is.
What would the most advanced levels look like?
The highest levels involve AI systems that can prove theorems autonomously,
Okay.
starting with simple theorems and eventually progressing to more complex ones.
Wow.
Imagine an AI that can not only understand existing math,
Right.
but also make significant mathematical discoveries on its own, perhaps even solving long-standing open problems in mathematics.
That's an incredible vision.
It is.
And what about auto-formalization?
Yeah.
What are the key milestones there?
For auto-formalization, the milestones focus on the quality and robustness of the translation process.
Okay.
The initial levels involve AI systems that can generate reasonable candidates for formalization,
All right.
with human feedback used to refine and improve the translations.
So it's like training an AI translator for the language of mathematics.
Exactly, and the higher levels involve AI systems that can produce accurate and reliable translations on their own,
Wow.
approaching human-level performance in converting informal math into formal proofs.
So there are clear benchmarks for measuring progress in these areas.
Right.
But earlier you mentioned this fascinating idea of conjecturing,
Yeah.
AI coming up with brand new mathematical conjectures.
You're right.
How do we even begin to evaluate success in something as creative and subjective as that?
That's a great question, and it highlights one of the biggest challenges in this area.
Okay.
How do you define interestingness in mathematics?
Right.
What makes one conjecture more valuable or insightful than another?
There's no easy answer to that. It seems like evaluating a mathematical conjecture would require a deep understanding of not just the logic of the statement, but also its potential implications and connections to other areas of math.
You're absolutely right, and that's why evaluating success in conjecturing is so challenging.
Yeah.
We need to develop new benchmarks and evaluation methodologies that capture the essence of mathematical creativity and discovery.
So we're really pushing the boundaries of what it means for AI to understand and do mathematics.
Yeah.
It's not just about crunching numbers or following rules, but about grappling with the same deep questions that have fascinated human mathematicians for centuries.
Exactly, and that's what makes this field so exciting.
Yeah.
We're not just automating tasks, we're exploring the very nature of mathematical reasoning and the role that AI can play in expanding our mathematical knowledge.
This has been an incredibly insightful conversation. It's clear that AI for formal mathematics is still in its early stages,
It is.
but the progress being made is truly remarkable.
It is an exciting time to be working in this field.
You mentioned earlier that this technology has potential applications beyond pure mathematics,
Yes.
specifically in areas like software and hardware verification.
Right.
Can you tell us more about that?
Absolutely. Formal verification is all about proving that a system,
Okay.
whether it's a piece of software, a hardware design, or even a complex engineering system, behaves exactly as intended. It's crucial for ensuring safety, reliability, and security in critical systems.
So instead of just testing and hoping for the best,
Right.
we can mathematically prove that a system will work as it's supposed to.
That's the goal.
That sounds incredibly powerful.
It is traditionally, formal verification has been a very manual and time-consuming process,
Okay.
requiring a lot of expertise, but AI is starting to change that.
So how is AI being used in formal verification?
One way is to use AI to automate the generation of formal proofs,
Okay.
which reduces the burden on human experts.
Gotcha.
Another approach is to use AI to identify potential bugs or vulnerabilities in systems even before they're implemented.
So AI is acting as a kind of automated watchdog,
Yeah,
helping us catch errors early on in the development process.
exactly. And the research paper outlines some exciting milestones for AI in formal verification,
Oh, yeah.
such as being able to verify entire software projects, handle complex security properties, and even assist in generating formal specifications.
Formal specifications?
Yeah.
What good.
Formal specifications are essentially mathematical descriptions of what a system is supposed to do. They provide the foundation for formal verification,
Gotcha.
defining the properties that need to be proven.
So they're like blueprints, but instead of physical dimensions, they specify the logical behavior of a system.
Precisely. And AI can play a role in helping humans write these formal specifications,
Okay.
ensuring that they are complete, accurate, and consistent with the intended behavior of the system.
It sounds like there's a lot of work to be done in this area, but also a lot of potential for AI to make a real difference.
There is, and this brings us to another important point. The need for collaboration between AI researchers, mathematicians, and software engineers.
Right. It's not just about AI working in isolation, but about AI working alongside human experts to achieve these ambitious goals.
Exactly. We need to develop AI systems that are not only powerful, but also user-friendly, transparent, and explainable.
Okay.
We need systems that can integrate seamlessly into the workflows of human mathematicians and engineers,
Gotcha.
augmenting their abilities and accelerating progress.
So it's a journey of co-creation and collaboration, where AI and humans work together to push the boundaries of mathematical knowledge and build more reliable, secure systems.
That's the vision.
It's an incredibly inspiring vision. But earlier we were talking about the challenge of defining interestingness in mathematics,
Right.
especially when it comes to AI generating new conjectures.
Yeah.
Can you elaborate on what criteria mathematicians use to determine whether a conjecture is worthwhile?
That's a great question, and one that has fascinated mathematicians and philosophers for centuries.
Yeah.
There's no single definition of interestingness,
Okay.
but there are some common criteria that mathematicians often consider.
Like what makes a mathematical conjecture stand out from the crowd?
Well, one important criterion is novelty.
Right.
An interesting conjecture should introduce something new to mathematics, whether it's a new concept, a new relationship between existing concepts, or a new way of looking at a familiar problem.
So it should add something genuinely new to our collective mathematical knowledge.
Exactly. Another important criterion is significance.
Okay.
An interesting conjecture should have implications for other areas of mathematics, potentially leading to new insights or breakthroughs in related fields.
So it's not just about solving a specific problem, but about opening up new avenues of mathematical exploration.
Precisely. And a third criterion that often comes up is elegance.
Okay.
An interesting conjecture should be aesthetically pleasing, expressing a deep mathematical truth in a concise and beautiful way.
So there's an element of art and beauty in mathematics as well.
Yeah.
It's not just about cold, hard logic.
Absolutely. And these criteria are all interconnected.
Yeah.
A novel conjecture might not be interesting if it's not significant or elegant.
Right.
And the significant conjecture might not be interesting if it's not novel.
So it's a complex interplay of factors that contribute to the interestingness of a conjecture.
It is.
No wonder it's so challenging to define this concept computationally.
You're absolutely right. We need to develop AI systems that can not only generate conjectures, but also assess their value based on these nuanced and often subjective criteria.
So it's not just about AI proving theorems, but about AI understanding what makes a theorem worth proving in the first place.
Exactly.
That's a tall order.
It is, and that's a major step towards developing truly creative and insightful AI mathematicians.
Okay, I'm starting to get a sense of the bigger picture here.
Yeah.
It's not just about AI as a tool for solving math problems, but about AI as a collaborator in the ongoing pursuit of mathematical knowledge.
Precisely, and that collaboration requires us to think carefully about how we design these AI systems.
What do you mean?
Well, we've talked a lot about the technical challenges,
Right.
but there are also important human factors to consider.
Okay.
It's not enough to develop powerful AI systems for formal mathematics.
Right.
We also need to make sure these systems are accessible and intuitive for human users,
Gotcha.
whether they're seasoned mathematicians, software engineers, or even students just starting to explore the world of formal reasoning.
So it's about designing tools that empower humans, not replace them.
Exactly. We need to consider the user experience, ensuring that these tools are easy to learn, efficient to use, and provide meaningful feedback to the user.
So it's a design challenge as well as a technological one.
Absolutely. And that's where collaboration and community building becomes so important.
Okay.
We need to foster a vibrant ecosystem of researchers, developers, educators, and users who are all working together to advance the field of AI for formal mathematics.
So it's a collective effort bringing together expertise from multiple disciplines to create something truly transformative.
It's an exciting time to be working in this field, and I'm eager to see what the future holds.
Yeah, I completely agree.
Yeah.
It's been fascinating to explore this intersection of AI and mathematics.
It has.
We've covered so much.
Yeah.
From the fundamentals of formal mathematics
Right.
to the potential for AI-powered mathematical discovery.
Absolutely.
And it's clear that this field is still in its early stages.
Yeah.
But the progress being made is truly remarkable. But before we wrap up, I wanted to pose a question to you
Okay.
and to our listeners.
Right.
We've talked a lot about AI proving theorems,
Right.
but what about the flip side? What about AI disproving things?
Okay.
Or even more intriguing, what about AI identifying potential flaws in existing mathematical arguments?
That's a fantastic point.
Yeah.
It's one thing to generate a proof, but it's another thing entirely to critically assess the validity of a proof,
Right.
especially when that proof might be incredibly complex and span hundreds of pages.
Right. It reminds me of how we were talking earlier about those informal AI systems
Yeah.
that sometimes produce outputs that seem plausible,
Right.
but are actually flawed.
Exactly. And that's where the rigor of formal mathematics becomes so important.
Okay.
If we can train AI systems to work within these formal systems,
Hmm.
they can help us scrutinize even the most intricate mathematical arguments
Okay.
and identify potential weaknesses or inconsistencies.
So it's not just about AI being a theorem prover. It's about AI being a mathematical skeptic,
Yeah,
constantly questioning assumptions
absolutely.
and pushing the boundaries of our understanding.
Exactly. And that kind of skeptical analysis could lead to some really interesting discoveries.
Oh, like what?
Well, AI might uncover flaws in long-accepted proofs, prompting mathematicians to revisit and revise those arguments.
Wow.
Or it might identify areas where our current mathematical frameworks are incomplete or inconsistent, opening up entirely new avenues of research.
That's a really exciting prospect.
It is.
It suggests that AI could not only help us expand our mathematical knowledge,
Right.
but also deepen our understanding of the very foundations of mathematics.
I couldn't agree more, and it highlights the importance of developing AI systems that can not only generate proofs,
Right.
but also critique, analyze, and even challenge existing mathematical knowledge.
So it's like we're moving towards a future where AI isn't just a tool for doing math, but a true partner in the pursuit of mathematical truth.
Exactly, and that partnership has the potential to transform our understanding of the world around us.
Well said. This has been a truly thought-provoking deep dive into the world of AI and formal mathematics.
It has.
A huge thank you to our expert for sharing their insights with us today.
It was my pleasure.
And to our listeners, thank you for joining us on this journey. We hope you found this exploration as mind-bending as we did.
I did.
Until next time, keep exploring, keep questioning, and keep diving deep.